Thank you for inviting me. Today I'm going to talk about how to solve LP faster. This is John with Aaron. Today we will talk about this problem. We want to minimize a linear function on a polytope ax greater than b. In here, I call m is the number of constraints and n is the number of variables. And usually you have a polytope, the number of constraints is roughly equals to the number of variables. That is the usual case in practice. However, sometimes you could have some object have much more constraints, for example this one, or something like matching polytope or something else. So in this research, we want to ask how can we solve those situations faster. And now I will talk about what is the previous result on this problem. Basically, almost all previous result is iterative method. What I mean is the algorithm look like this form. The algorithm will start with some initial point, and then if that point is not optimal, then you improve that point until you get to the optimal point. And the total running time is the number of iterations times the cost per iteration. And in this talk, I will only focus on how many iterations we need to solve LP. And in the next talk, he will talk about how much it costs for each iteration. And here we call algorithm efficient if each iteration is polynomial time, and you don't need to use LP solver in each iteration. Otherwise, I have a one iteration LP solver. So, yeah. So let's see what is the previous result. In fact, there is much more previous result. I just select some to show it here. The first result is simplex method. The number of iterations is exponential, but usually in practice it's really good. And the second result by Kachan is the ellipsoid method. This is the first polynomial time algorithm for LP. And then this method is by Kamaka. That is the first interior method. It takes m iteration and it improves by 1 to square m. After that result, all result, the exponent there is still 1/2, but people try to see how to improve m to n. And the first result by y there, he improved to mn 1/4. And then finally, let's get the result square n. And in certain theory, this is the best result you can do using interior method. Notice there is two things. One is, every result is square root, and the first result is by 1. And the second thing is, let's get square m, but this is not efficient. I will tell you later why it's not efficient in my sense. And in our result, we cannot exactly get square m, but we get with some polylog term. And then to solve Maxwell, we need to improve square root n to square root rank. In next talk, everyone will talk what do I mean by square root rank. And both methods is efficient. So we marked last year. So for certain LP, such as unweighted Maxwell problem, in fact, he can design an interior method that runs in m to 3/7 iteration. So it's better than square root, but this is not for general LP. And the talk outline is something like this. I will explain the Wernicke algorithm, because that is the easiest algorithm in the interior method. And then I will show why square n is possible. And then I will show, in fact, our result is inspired by the YD algorithm. So I will explain the YD algorithm, and we show how to improve the YD algorithm to square n. So in this talk, I will not try to use the standard way to teach about interior point. I will use my way of thinking. So it is not standard. But I hope you like that. You can think instead of, in this talk I will think about solving an LP is like maintaining a center of a polytope. For example, say somehow this is the polytope and you want to find that point. And say each iteration, in the first iteration, you somehow get a center. I didn't define center here now. I will define it later. Imagine, for example, a CG or whatever center you like. And then each iteration, you first put the constraint there. When you put the constraint there, you change the polytope, so you need to update the center. And in each iteration, you want to move the constraint closer to the optimal point. And each step, you need to maintain the center. Say, if each iteration you can move the constraint by theta portion, then after 1 over theta iteration, you solve the LP. So the whole problem is how can we define a center such that we can move the constraint as much as possible. But why we need a center, or what is center? For example, if you don't do anything like this, each time you just keep pushing the constraint, and then until you hit the current point, then you may not know what to do. Then maybe you do some silly stuff, and then it looks like a simplest method. It could work in practice, but it's quite difficult to prove anything. So you can think the center is try to use some global information to avoid bad decision. So because just not to confuse people, I try to say the algorithm again. Here I assume the optimal value is 0 for simplicity. Then say we start with value t is very, very large, and we find a center for that polytope. Our goal is to find c transpose x equals to 0 and ax greater than b. So we start with a polytope, we can find a center. Then each iteration, when t is larger than 0, then we decrease the t a little bit, and then update the center for the new t. This is the rough outline for the algorithm, a general framework for the algorithm. And this is usually called interior point method because each iteration you maintain an interior point of your polytope. And some people may ask, because finding an initial point is equivalent to solve LP, but in fact there is general trick to deal with that situation. For example, if ax greater than b, you cannot find any point, then you can consider ax greater than b minus 1 million. Then it's easier. In fact, you can choose some constant there. You can always find an initial point. So there is not a problem. Yeah. So then, how should we define a center? The usual way to define a center in interior point method is via a function. Say we are given a function on the polytope. That is a convex and smooth function, and we assume the function will bow up on the boundary. We call those functions is barrier function. For example, the standard function they use is called standard log barrier function. It is summation of log s. For example, we want to evaluate the standard log barrier function at that point. Then the s is the distance to your each constraint. We call those a slack. And then the standard log barrier function is you just sum up the log of the slack. And we define the center is the minimum of the barrier function. Yeah, so we now have a center. Then what are the group center allow us to push the constraint as much as possible? It turns out the key property is about rounding. From now on, I will always assume the center is induced by a barrier function p. And this is the center. This is the minimum point of the function p. Because that is a convex function, so locally the contour line is look like ellipsoid. If you enlarge your ellipsoid until it touches the polytope, you get the first ellipsoid. When you continue to enlarge your ellipsoid, you will cover the whole polytope, you get the second ellipsoid. And we call that ellipsoid is a lambda rounding if the ratio of two ellipsoid is lambda. And there is a standard theory about self-concordant barrier function. I will not give you the formal definition, but I will only give you the geometric meaning. We call a barrier function P is lambda self-concordant if P is smooth. why we need the barrier functions to be smooth. Imagine if the function is not smooth when you push the constraint, then the function keep changing the path, then we don't know how to maintain our center. That is bad. The another property that I will emphasize in this talk is P give a lambda rounding. For example, this is a bad barrier function if the local ellipsoid look like that thing.
When you said you have an ellipsoid corresponding to P at x, you're just taking the Hessian?
Yeah.
Okay.
Yeah.
Okay.
Yeah, so the standard theory is
So is that equivalent to the standard definition in terms of third derivatives and stuff? The definition you just gave?
this is a necessary condition, not a sufficient.
Is it for interior point or not? Is this condition alone sufficient for...
No, necessary only. No. Yeah, the standard self-concordant barrier function only implies this, but this doesn't really imply that one. But this is the geometric meaning I want to convey. Yeah, so you can rethink my center alpha look like this. Each time the barrier not only give you a center, also give you an ellipsoid that approximate your polytope. So you can think the framework I propose is look like this. Each time you move the constraint and the new barrier function give you a good rounding of your polytope. So you can think the algorithm is trying to approximately know what the polytope you are trying to optimize. But why? Oh, I missed a slide there. And then given a lambda self-concordant barrier function, then the theory will give you an algorithm to solve interior point in square root lambda iteration. But why is square root lambda? However, in this talk, I will try to avoid any proofs. I will avoid any equation proof, so I can only give you a lambda proof. Yeah. Anyway, so if you don't like a general barrier function, then you can always think about P is the standard log barrier function. For this slide, you just need to believe me. For Newton method, assuming those certain smoothness assumption, then if you are given any point that is not optimal but within constant error to the optimal point, say Py is less than the minimum plus 0.5, then Newton method will give you a way to find the minimum point in constant step because of certain smoothness assumption I didn't tell you. And so you can, and then now I call the Y is the O center. This is the O center, this is the constraint, original constraint, and you want to push it. And again, by the smoothness assumption I didn't tell you, when you push the constraint a little bit, then the first equation, P new Y minus P new minimum P, this is the error when you are using the O center. And we want to remember in the last slides, I promised you whenever the error is less than a constant, then you can find the center. So each step, what you can do is you can push the constraint such that the O center still give you a constant error for the new center. If this holds, then you can use Newton method to find the new center. So in fact, you just do some algebra, you can show, in fact, that is bounded by, this is the new constraint, that is the old constraint. And if you push it to here, then I call the ratio is, this is the new gap and that is the old gap. When the new gap over the old gap is constant, then the old center approximate the new center very well. So you can find the new center by Newton method. But then now the problem is then, do we know the gap is small? I mean, imagine if your new center is here and you want to push that way, then the thing you can move is very, very tiny. So now comes with the rounding assumption. because we know the Berry function gives you a lambda rounding. For example, you have an ellipsoid here. I just call it radius 1. And then we know from the Berry function that gives you a lambda rounding. That means that ellipsoid, when you enlarge by lambda, this covers the whole ellipsoid. So for example, if you want to push that direction and say this is the optimal value, then we know the distance to the boundary is at least 1 because there is a ellipsoid radius 1 inside. And we know the distance here is at most lambda because you have a lambda ellipsoid cover the whole thing. And so each step you can move constant compared to the whole distance. And this gives you the proof why is lambda iteration. Any question here?
I'm a little confused why the ellipsoid that contains the particle also matters. Is there some intuition why that happens?
Imagine, say this look like hypercube, and each iteration, the problem is the usual little method, you only allow to move inside certain ellipsoid. If each iteration you only allow to move the distance like that one, then you least square n step to there. Yeah.
I'm sorry, say that again? What would you say?
Say here, when you move, the worst case is we can only move constant. But here, that is very far away, is lambda far away.
And that might be,
Yeah, that may be a trouble.
that may be the optimal point, and maybe way over there or something?
Yeah. So you need to push a lot of time.
You're saying that the properties of Newton's method is that if you're sure that it's not going to jump out of the entire polytope in the first place, then you know it's going to basically stay in the ellipsoid. That's
Yeah.
Okay, and therefore if that ellipsoid is too small, it's going to take you a long time to move across.
Yeah.
So where's the square root coming from?
Yeah, the leg size. Yeah. Basically, I'm not able to show you because I don't have a good picture to draw. But basically, the previous proof, we measure the progress by the distance from here to here. But turns out the correct measurement is the here to here. And then you just do some algebra. In fact, you can prove this gap is ON approximate the real. I don't know how to say it anyway. Yeah.
You're killing us, man. It approximates the real what?
Approximate the real duality gap. In fact, if you use the standard log Berry function, then this gap is the real duality gap over n. Yeah. So that is a natural thing to do.
Sorry, I was just kidding.
Yeah, so roughly speaking, you can think whenever the Berry function is smooth and give you a lambda rounding, then you get a square root lambda iterations.
Let me check this with my memory of Renneger's algorithm, where I thought the way he got the going from lambda to root lambda was by treating the constraint plane that he was adding as if he had a root lambda multiple of it.
Yeah.
So that it factored into the barrier function more times.
But
Is that compatible with this?
in both cases you can also prove that. You can, just if you would add multiple of that, then the proof look nicer.
Okay.
But you can still prove for this version. Yeah.
The version that Yintat was saying was more along the lines of that you have to use a primal-dual potential function, and the square root is coming from doing something primal-dual.
Okay.
Drawing primal-ish pictures, and that the square root is coming from being able to update your duals too.
In my way of thinking, the reason of square root lambda is, in fact, to really get square root lambda, you need to push more than that point. But however, you can imagine when you push you push the constraint there, you can expect the point will go that way. So even you push beyond that point, in fact, you are still not touching the center. So you can prove, in fact, you can push that much. But but that requires more calculus. Yeah, so let us see why the standard log Berry function is bad. Remember, the standard log Berry function is the sum of log of the slack. You can imagine the center is like you put a magnet on each constraint of the polytope, and then your point just repose away from each magnet. Then the reason the analytic Berry function is bad because you can repeat certain constraint by m times. Then you are like putting m magnet there, then your point will push away. Then here you will get pushed away by here like 1 over m there. So the rounding here is really bad because the ellipsoid locally here look like this one. You need to enlarge m times to cover the whole polytope. But is that a tight reason why this is bad? Because we know in practice usually it takes less than 60 steps. In fact, Misulu, Tor, and Yi show that if you start with a random polytope, usually the first step you can progress a lot. So if in fact many people try to come up with that Berry function is bad a lot until this year Matt and Talaki, so in fact you need square m step. They construct a counterexample, m is in fact exponential to n, and the integral method leads to take exponentially many steps to visit every vertex of the hypercube. So in fact the square m is tight for that Berry function. So and now I will talk about then why we believe it could be square n. Yeah, in fact, Limerovsky and Ellipsoids show that this Berry function gives you ON self-concordance. That means using this Berry function to solve LP, you get a square n iteration. And just to give an iteration for that Berry function, the Berry function is look like, say, each time you have.
What is that? I mean, there's a little O up there.
Yeah. I was planning to draw. Say you have the convex set look like this, and then say your current point X is here. Then you consider the polar of the convex set around this point, which I cannot really draw. Something look like this. Whenever your point is closer to the boundary, then the polar will become larger. So this Berry function will go up when you close to boundary. And the reason why this Berry function is good, because the Hessian of this Berry function roughly equivalent to the second moment of this matrix, the polar of your convex set. And we know from Cannon, Noas, and Simonovich, for any convex set, if you look at the second moment matrix, the second moment matrix will give you an ON rounding. So you can imagine the second moment matrix give the ON rounding of the polar set, and you can take the polar, and then you will get back the ON rounding of your origin set. And this is the reason why they get ON self-concordance. However, this Berry function is a little bit difficult to compute. Let's see why. At least for now, the only way I know how to compute second moment matrix is to compute poly many time sampling on the polar polytope, the polar convex set I mentioned. We need to compute second moment for that one, so you need to sample point randomly in that set.
And log n.
Yeah, I just don't want to be precise. And then to get one sampling, you need to do method chain that is still polynomial, so this is still good for our definition of efficiency. But the major problem is to compute one step of method chain. You need to implement the separation oracle for this set. And the only way I know how to implement the separation oracle is to solve an LP on that convex set. So you are requiring to solve the similar LP. You didn't reduce the dimension or what. So So this Berry function basically asks you to solve polynomial many similar LP, and that's why we call it log efficient. So the major open problem is how can we get a ON efficient self-concordant Berry function, and in these results we get O tilde n. Yeah. And our result is inspired by the volumetric Berry function defined by the ideal result. The volumetric Berry function is look like this. The PS is the standard log Berry function. Then you can imagine. Now you start with the standard standard log Berry function. Then you take the Hessian. That means you look at the ellipsoid around that point, and then you compute the volume of that ellipsoid, and then you take log. And why did I say you mix up with the original Berry function? And he said this is a good Berry function. By the way, this is volumetric because you're computing a volume of some ellipsoid. To see why this is good, we need to look at some example. The same example before. This is the previous case, the log Berry function. If you put m magnet there, it will push here. The distance is 1 over m. But you can imagine the volumetric Berry function look like this. Instead of permanent magnet, they put some electric magnet here. I will explain in the next slide why it's an electric magnet. But you can just try to compute for this Berry function. The distance here is 1 over m to 1/3. Yeah, I will explain next slide why it's electric. And in fact, why they are able to prove this Berry is a mn square root mn Berry function. So you take the so if you use this to solve LP, you get mn to 1/4. And to see why the volumetric Berry function is good, we need to do some calculus. Say around any point in your convex set or polytope, then you.
What is PS of x? It's the standard variant.
Yeah, PS is the standard. And we try to around at any interior point, you try to approximate your volumetric Berry function by a certain weighted log Berry function. In fact, any Berry function you can write in this form because you just take the Taylor expansion and you choose the weight of the weighted log Berry function such that first derivative match the original one. You can always choose weight such that it happens. And turns out you can think the volumetric Berry function is like choosing a weight of this form, sigma plus n over m. And sigma is Leffe scores. I will explain here. You can imagine Leffe score is a way to measure how important is a certain role. Just to illustrate, for example, for this matrix B, if you put it into this formula, then you will get this constraint is very important. The importance is 1 because this is only represent. It doesn't represent by other constraints. And those two constraints is less important, but this is more important than that because the number here is larger. For example, like this. And there is, in general, we know the Leffe score sigma is always between 1 and 0, and sum of Leffe score is the number of variables. And whenever you repeat certain constraint 1 times, then the Leffe score of that constraint will decrease by 2. Yeah, so you can imagine this is a way to measure how important is a constraint. And now so you can think the volumetric Berry function is trying to look at your constraint matrix and then see how important is each row, and then we weight the Berry function by that importance. That's why I put the electric magnet there. You can change the magnet tail. And to look back on the original Berry function, to look back at the previous examples, imagine you have a 0-1 interval and the 0 constraint repeat k times. Then if you say your current point is in the center, Then if you put in that formula, that means you need to compute what is the slat inverse A. When you are at the center point, every slat is 1. So the slat inverse A is level 1 matrix.
Sorry, so what is the SY inverse matrix?
S is the slat measured at the point Y.
And the matrix?
It's a diagonal.
Diagonal matrix. Yeah. When you are at the center point, then every constraint is equally important. Then the barrier function will push you to there. But when you are closer to this constraint, then suddenly, because the slat here is smaller, the slat inverse is larger. So the leverage score of this rule will become larger. So when you go close enough to this point, then the magnet will strong enough to push to balance at that point. That's why this barrier is slightly better than the standard log barrier function. Now we can look at our barrier function. Yeah, basically, the first sentence is the previous volumetric barrier function. This is like you start with, if you think about it a little bit more, you can think the wider result is showing, given the standard log barrier function, you can take log determinant Hessian of that function and get a better barrier function. So there is no reason you should stop this process. So how about if you define a process to create the barrier function by one step, and then see how good is that. However, this formula is pretty difficult to analyze, so we do the analysis like the previous slides. Say, imagine your PK, your previous barrier function look like a weighted log barrier function, and then do the calculation again. Then you will notice at around any point y, then the new barrier function will look like this form. You look like to reweight your constraint by sigma plus n over m. Notice the constraint matrix is not S inverse A, is square root W S inverse A. That's why it depends on the previous barrier function. And then surely, then what is the lateral object is, so you can think each step we update the weight by this equation, and we want to understand what is the limit of this barrier function. So we define object P infinity is just whatever weight satisfies this equation, we just ignore that term.
So, the way of this recursive formula, I would expect that if this n over m in front of ps of x, doesn't that compound as you go?
Oh yeah, so you need you need to reweight.
No, but it looks like it. Oh, there's that going into the weight. I'm trying to figure out why you kept having the log of si times n over m as opposed to.
Yeah, at the end, after k step, you should divide everything by k, then you get sum of weights is n.
Okay.
Yeah. Yeah, that's why the final equation I omit that term.
Okay.
Oh, this is a typo. This is the previous weight.
Okay.
Yeah. Yeah. So what is that object? So now you can imagine. So now we start to understand what is that object. The W is the leverage score of the matrix we weight by W. If you guys have seen the talk by Richard Pan, you will remember this object. Anyway, I would.
So should there be an n over m in the top line or not?
This is weight. This is typo. This is weight.
But the first place is an n over m up there.
Yes.
Should it say that or not?
Yes.
There is many typo there.
Are all of those n over m?
This is the weight. There is low n over m. I mean here.
For P1 plus K.
Yeah.
N over m is just to make sure that all one's vector is normalized and then just taking
Yeah.
after.
Yeah, there is low n over m there. Should I write in that box?
No, it's too late to ask.
Anyway, yeah, so we go to next slide. Nothing happened. Yeah, remember we want to understand that object weight equals to left face cos. To understand that object, we ignore the slack for a moment. We try to divide the term there. If the weight is not 0, we can divide. We define it as the tau. We try to understand what is tau. Now assume there is no slack. Then you say take a look of this polytope AX less than 1, and then look at the ellipsoid. Look like this form. In fact, the distance from there to there is 1 because there is less than 1. Is it? Yeah. And then turns out you can compute tau is measuring that distance. So what is that equation telling you? When every tau is less than 1, that means the ellipsoid is inside this polytope. And turns out you can think this condition is trying to make the ellipsoid as large as possible such that either W is 0 or it touches the polytope. In fact, this is the automatic condition for joint ellipsoid. So you can think the limiting weight is representing the joint ellipsoid for this polytope. This is the polytope. Any question? Yeah, so now look at the, remember our Berry function, the recursive definition is each time you replace the Berry function by log that Hessian of the Berry function. So you can imagine the final object also satisfy that equation. And then you just put in the formula for the Berry function. Remember our Berry function will look like a log Berry function, weighted log Berry function. So the Hessian will look like that form. And remember that is the joint ellipsoid. So the whole formula is just computing the joint ellipsoid of S inverse A x that polytope, and turns out you can draw the object like here. This Berry function is look like you start with a polytope at certain point x, you symmetrize your polytope at that point, and then you compute the joint ellipsoid of that intersection, and then compute the volume. And this is the Berry function you get when you repeat the YDA process. But this Berry function is not perfect. In particular, this is not smooth. For example, you imagine, so the Berry function is look like each time you compare a joint ellipsoid, but joint ellipsoid is not a smooth object. For example, this example, if you try to push the constraint down, originally the ellipsoid doesn't touch this constraint. But when you push it down enough, it suddenly touch this constraint, and then it will change the direction because it loads some new information. So this is not a good Berry function. And numerically, you can think numerically you can write down the joint ellipsoid Berry function in this formula. And this formula have a problem because of this constraint W greater than 0. Or you can think because this is not a strongly concave function, so the optimizer is not smooth. So let us recap what I am saying. Whenever you use the standard log Berry function, it gives you square M iteration, and then the y they propose the volumetric Berry function, it looks like you do some process on the original Berry function, then you get this. This gives you Mn to 1/4. And then we just suggest we should repeat that process until you get converged to some answer. Then you get the joint ellipsoid Berry function. But this Berry function is not smooth. So how should we do it? Anyone know what should we do when the function is not smooth?
Add the volumetric barrier to it?
The answer is to regularize.
Yes.
Yeah. Basically, in our paper, we regularize in that way. We raise the power W to certain power. In another way to see it, you can think you raise the power on this term. Then originally your constraint is a simplest, become is less simplest, so this is smoother. Anyway, because some people don't like we raise the power of that thing, so in fact you can also do that, but we didn't do it in our paper. You can just put the entropy term there, because this is strongly concave, so everything is good. But we still explain this because it relates to the Japan talk. I will explain later. Yeah. Oh, yeah, I explain here. And in fact, when we write the paper, we don't know why we raise the power. We just notice when you raise the power, you get some better property. And turns out it's related to a so-called LP Lewis race. Thanks to Cohen and Penn, we know it's a very important object. For example, if you are given a matrix B and you consider a weight satisfy that equation, then Richard Penn already told us you can resample your constraint such that it can give you a smaller matrix approximate your polytope. So in some sense, you can think our interior problem method try to use those weights to help you solve LP. Although it cannot use for sampling, because in that case, in our case, P will be log M. So here, if we really, really large, we cannot use it to sampling, but we can use it for solving LP. You can think our result is like that. Also, there is geometrical meaning of the Lewis rate. You can think Lewis rate is trying to find the maximum volume that is almost inside your polytope. But the definition of almost is it satisfies certain P moment constraint. When P is infinity, then as we discussed, it is exactly corresponding to the joint ellipsoid. And in the Richard Penn talk, they show how to compute the Lewis rates for P less than 4. And certainly our paper show how to compute Lewis rates for P equals to infinity. And the way is, there is multiple ways to do that. The wider paper somehow give you the way is like this. That is the previous recursive definition of the rate. In fact, you can prove you need to normalize the rate, and then you can show it exactly converts to the L infinity Lewis rate. Or you can say the W gives you the joint ellipsoid. And recently, we together show in fact you can extend that formula to P greater than 2. So now for any P, we can find the Lewis rate. And so, and this is the reason why our Berry function is computable, because we can compute those weights. Yeah, so just to do the conclusion, for any polytope, you can consider this Berry function, and then the main theorem is this gives you square n iteration alpha to solve LP. In picture, you can think each iteration you move the cost constraint, and then you remove a regularized version of joint ellipsoid. Look like this. And notice that in this talk, I didn't tell you exactly how to do every calculation. And the main goal of our research is to find an LP solver fast enough to solve Maxwell to make a better Maxwell alpha. However, this approach has two problems now. Is first, you cannot write Maxwell in this way with only m variables, because you need a variable for each edge, so there is m variables. Also, if you look carefully, when you compute the leverage score, you need to compute a matrix look like that, and this is too slow for graph problem. So in next talk, everyone will talk about how to fix that two problem. Yeah, thank you.